Welcome to the 14th lecture on the NPTEL course on computer system optimization for machine learning. Again, we will go over a brief recap and then we will continue the discussion on DNN accelerator. So, in the last class we started discussing on DianNao, which is one of the earliest accelerator for DNN models. One of the main concept of this accelerator is tiling to reduce memory usage. So, remember the concept of tiling is we do not need to fetch or we do not want to fetch all the activations multiple times, rather fetch the activations in tiles and then finish the computation corresponding to each of the tile at one go, finish all the computation corresponding to one particular tile at one go. So, this was the result we saw, that as a result of tiling the memory bandwidth required for input activations are becoming very low with respect to the case where there was no tiling, and then if we use tiling plus L2 cache, then the memory bandwidth requirement for the synapses, which are nothing but the weights, that also becomes low, right. So, now we will see more details of the hardware implementation. So, remember when we talked about this fully connected layer, so we have neurons, right. So, neurons are nothing but they are performing multiply and accumulate, correct. So, that is the only operation these neurons are computing. Now, one very naive hardware implementation is we can fully lay out the neurons and the synapses on the silicon. So, we can say that if there are like 16 neurons or 8 neurons or whatever, if there are like n number of neurons, we can make tiny neuron blocks and we can fabricate that on that silicon. So, you can think that each of the neuron block will take one weight and then it will perform multiplication with respect to the input, and then it will do some addition or they will be separately added, right. That is a very naive implementation. So, neurons can be implemented as the logic circuit performing the computation, synapses can be implemented as the latches or RAM storing the weights, and then we can implement the nonlinear function as a piecewise linear function, right. So, again that is a very naive implementation. Of course, the biggest advantage is the speed is very high, because in this case if we have this naive implementation, the distance travelled by the data is less, right. So, whenever one input neuron, or so this is the example, let us say this is the hidden layer, and then whenever the hidden layer is computing something, or whenever some input neuron is computing something in the hidden layer, then it is going to the next layer immediately. So, it does not go to the main memory and then come back from the main memory. So, the distance travelled by the data is less, correct. That is the advantage. But of course, I mean by now you might have figured out, but there is a big disadvantage, which is the area increases drastically with the increase in the number of neurons. So, first of all, if we have this kind of structure, then we need to have like so many neuron unit or so many these logic circuits to implement a big DNN. So, remember when we were discussing different parameters of the state of the DNNs, we saw that the number of parameters can be in terms of billions, right. And then if we have this separate logic circuit for each of the neuron, that means we will have to have billions of logic circuit. That is nowhere possible. If we do that, the area of the whole chip or the area of the whole accelerator will increase drastically, correct. Now, this is the result. I mean if we really do that kind of hardware implementation, then we can see what is the implication, right. So, the main implication is the area and energy suffers a lot with increasing number of input and output neurons, right. So, this particular figure is showing three hardware parameter. One is critical path, which defines the frequency, the maximum frequency or the maximum operating frequency is nothing but the inverse of the critical path. Then area of the hardware, and then the energy consumption of the hardware. Okay. So, that is being shown in this figure for different types of fully connected layers. So, whenever we say 32 by 32, that means there are 32 inputs and 32 outputs of the fully connected layer, right. So, as you can see, and then again if we have 32 by 32 fully connected layer, that means the total number of synapses is 32 multiplied by 32, which is 1024. Total number of weight is 1024, right. Now, if we have that naive implementation, then as you can see that the critical path increases probably linearly, you can think that it is increasing linearly, but if you see the energy is increasing like exponentially. There is a huge increase in energy, right. Not only that, the area, sorry, I think I messed up something, yeah, the area is increasing exponentially, but at the same time energy is also increasing exponentially, right. So, that is a huge increase in energy as well as area if we perform this or if we have a hardware which has a naive implementation of this fully connected layer, right. Now, that is not intended, right. We should not have that kind of hardware, and that is why DianNao proposed some specific hardware. It has some specific accelerator architecture which is tailored for deep neural network applications, or specifically it is tailored for this fully connected layer, right. So, at a very high level, it has the DianNao architecture or this accelerator architecture has some storage. The storage is NB in to store the inputs, SB to store the synapses, and then NB out to store the partial sums, to store the output. And on the computation side, it has 3 unit, I mean they call it neural functional unit for the whole computation engine. Neural functional unit or the NFU is segregated into 3 different unit. One is NFU 1, NFU 2 and NFU 3, right. So, NFU 1 is nothing but a set of multipliers, NFU 2 is adder tree, and then NFU 3 implements the nonlinear function or the nonlinear operations, right. And finally, they have control instructions which is the software part of the this particular architecture or this particular accelerator. So, now we will go to the each of these components, storage, different NFU and control instruction, and then see how this accelerator architecture is tailored for deep neural network applications. Now, let us first discuss about the storage. Okay. Now, for the storage, so usually remember when we have our regular computer, we have L1, L2 cache and then DRAM, etc., right. Now, whenever we put some data, it is mixed with other data, correct. I mean there can be multiple application which is writing onto the L1, L2 cache or the DRAM, etc. So, all the data is mixed, correct, and that is why we have like fetching policy and all those things which takes time and so on and so forth, right. Now, in this particular accelerator architecture, they have split buffers. By that we mean that there are 3 different buffers instead of a single cache. So, one buffer is for to store the input, one to store the weights and one to store the output, right. Now, if we have 3 different buffer for 3 different parameter, then it will result in reduced conflict, because now if we have a separate buffer for input, then only the input activations will stay in the buffer. If we have a separate buffer for synapses, then only the weights will be staying in that particular buffer. Similarly, like if we have a separate buffer for output, then only the outputs will be stored there, right. So, if we have this reduced conflict, now I mean if we have this I mean in our usual setting of CPU or GPU, in the cache maybe all the inputs, weights and the outputs are mixed, right. I mean that is why there is a conflict, and then at the end whenever we are accessing, the access time is high, right. So, since they have implemented the split buffers, there is a reduced conflict and then the access time is also less. That is one of the advantage of this split buffer. Now, these buffers are implemented as scratchpad memory, which is like lower cost, and then another important point to be noted here is different buffers has different width. So, you can see that NB in, NB out and SB has different width, and that enables reading of different width of the data, Okay. So, let us discuss more about the storage. So, here the NB out is a circular buffer. Now, remember whenever we perform the tiling, if you remember, we were computing the partial sums, right. We are computing the partial sums for S0 and S1. So, in this case we will have S0 and S1 if the number of output is 2, we were computing the partial sums with the tiling, right. Now, that means whenever we come back to the next tile, then the corresponding outputs needs to be added to the partially computed S0 or S1, correct. So, that is why this NB out is implemented as a circular buffer. So, partial sums are pushed into the NB out instead of sending them back into the main memory and fetching them again. Now, output is read from NB out only when all the input neurons are integrated and for the partial sum. So, see there is a feedback from NB out, there is an arrow to the adder tree, which that means we are adding the head of the buffer. I mean in the head of the buffer, the expectation is we will have the partial sum. Now, with that partial sum we will add the newly computed sums or newly computed partial sums. So, that is why this NB out is a circular buffer. So, remember, I mean let us say we have this input activation, right, or maybe you can think that these are the tiles of input activations, correct. So, let us say one entry is nothing but one tile, right. So, this one entry will get multiplied with this T n by T n, or one tile will get multiplied with this T n by T n, and then we will produce one output, right. And then the next tile will again get multiplied with the T n by T n. So, we will produce another output. So, let us say first output, let us say the circular buffer has just 2 slot and this is the head of the buffer. Okay. So, initially it will be produced I mean the first tile will be fetched and then it will be computing first tile will be fetched, it will be multiplied with the weights, and then let us say S0 is computed, right. So, S0 is computed and it will be kept here. Then in the next cycle S1 will be computed, and then since it is a circular buffer, in the next cycle S0 will again go in this position, S1 will go in this position, right. And then when S0 comes here, it is the time to add with respect to S0, because at that time we have already fetched the next tile, right. And remember, this S0 and S1 are the partial sums. So, that is why if we have this partial buffer or circular buffer, then we do not need to put these partial sums back into the memory, rather we can seamlessly add to get the final product, final output. So, that this is very useful when we are performing the tiling, right. Now, we have NFU, as you can see there is there are 3 NFU, neural functional unit 1, 2 and 3. The NFU 1 consists of multipliers. Now, I mean as we have already seen and we have discussed many times, the convolutional layer requires multiplication, right. Now, in this particular work they have implemented 16-bit fixed point multiplication rather using 32-bit floating point multipliers, right. So, let us see what is the advantage. Now, of course, when we say 16-bit fixed point multiplication instead of 32-bit floating point multiplication, we can assume that we are losing some precision, but then in terms of DNN you can see that the error is almost the same. If you see this particular figure, you can see that the error is almost the same between floating point and fixed point multiplier. But then there is a benefit, there is good benefit in terms of hardware. Okay. So, you can see for the 16-bit truncated fixed point multiplier, the area is 1309 micrometer square and the power consumption is 576 microwatt, right. Now, when we have 32-bit floating point multiplier, then the area is like 6 times and the power is almost like 7 times, right. So, that is a huge gain in terms of hardware. Now, here you can see that we are getting this much huge gain 6x and 7x without almost losing anything in the accuracy. So, that means we can actually have 16-bit fixed point multipliers instead of 32-bit floating point multiplier. So, all these multipliers are implemented using 16-bit fixed point multipliers. Now, the second neural functional unit is the adder. So, the adder here is not a basic adder, rather they have implemented using adder tree. Now, one advantage of adder tree is that they have less generate and propagate. So, they have less latency. Okay. So, adder tree is very common in digital circuits when we have to add many numbers, right. So, as you can see that we have this multiplication, I mean in terms of partial sum, whenever we have partial sum, if we have like lots of output, then the, or I mean not lots of output, if we have lots of synapses, then we have to add all those ai multiplied by wij. So, and then get the final output here, right. So, that is basically the advantage of adder tree, because there are less generate and propagate if we have too many numbers to add, right. And then finally, they have nonlinear unit, which involves the nonlinear operation like power of, exponential, division, etc. We already discussed all these nonlinear operation like ReLU, sigmoid, etc. Now, remember when we have the hardware, hardware only can do like, hardwares are nothing but logic gates, right. They can have like AND or NOR gate. From all those gates we can have adders, multipliers, like those basic arithmetic operation unit, right. Now, with that unit, how can we build a nonlinear unit, or how can we perform nonlinear operation? So, in this particular accelerator architecture, the nonlinear unit is implemented as piecewise linear function. So, let us say this is the sigmoid function, which is a popular nonlinear unit used in many DNNs. The curved one is the sigmoid function. Now, it can be approximated with a piecewise linear function. So, the piecewise linear function says that from this point to this point it is 0, from this minus 2 to plus 2 it has this linear, it is approximated as this line, and then again after that it is taking the value of 1. So, that is the piecewise linear function. Of course, it will lose some accuracy, but then they show in the paper that the ultimate accuracy of the DNN remains the same. Now, of course, we can have more pieces of the linear function. So, we can say that we want to approximate like this. So, we can have more than like in this case we have 3 pieces, we can have more than 3 pieces, more number of pieces will give us better approximation, right. So, the nonlinear unit in this accelerator architecture is actually implemented with a piecewise linear function. Now, finally, any hardware, whenever we have a new hardware or whenever we have a new accelerator, that hardware or that accelerator is never complete with the software. Like for an example, we have GPU, yes, we have NVIDIA GPU, AMD GPU, Intel GPU, etc. But then you do not go and program the GPU, you just write a piece of code, right. So, there are underlying software. For NVIDIA there is CUDA, for AMD there is ROCm, from Intel there is OpenVINO. All these softwares are actually helping the user, so that the user can just write a piece of code and then it can automatically be mapped onto the GPU, and we will have the expected output with expected result, right. So, similarly, in this particular accelerator architecture in DianNao also, the authors proposed a bunch of control instructions. So, you can say, you can think that it is nothing but the instruction set, right. So, this is the format of the instruction. So, you can see there is instruction for the synapse buffer, NB in, NB out, NFU, and each of the entry shows what to put for that particular like hardware component. Like for synapse buffer, we have to first put what is the read operation you want to do, whether we are doing reuse or not, what is the address, what is the size. For NB in also read operation, reuse, stride, etc. right. And then when we launch this bunch of instruction, the result of this bunch of instruction is one fully connected layer. So, this is the example of this is the set of instruction, or this is the example set of instruction when we have T in equals to 8192, T out equals to 256, and then if we have 64 entry buffers. So, again I mean I am not going into the details, you can go ahead and read the paper to know more details about the control instruction, but at a very high level, whenever any company proposes a new hardware accelerator or new architecture, they have to accompany that hardware with the software. Okay. And that is why I mean GPUs are on high demand. If the GPUs did not have a good software, they would not have this user friendly, and then they would not have become like this much usable, right. Now, finally, this DianNao is a I think it is a fabricated chip, and they are showing the results. I think this is the synthesis output, or maybe the post routed output, I am not sure, but this is how the chip looks like. So, you can see this is a square chip, and then they have annotated the different portion of the chip, where this part of the chip is taken by the input buffer, this part of the chip is taken by the output buffer. This part is for the neural functional unit, where they have 3 components: NFU1, NFU2, NFU3, multiplier, adder, and the nonlinear unit, and then this part is consumed by the synapse buffer, and then this tiny part is consumed by the control instruction, or the control buffer, or the instruction buffer you can think of, right. Now, this table is showing the actual area of different component of the chip, right. So, if you look closely, the synapse buffer is taking 22.65% of the total power and 38.17% of the total area, right. So, not only that, this synapse buffer is taking 38.1, then NB in the input buffer is taking 14, NB out is also taking another 14, right. So, if you add them, it will come about like 70%, right. And then this NFU, the computing unit, is taking 28%. Now, here the main takeaway is, we can all think that all these machine learning algorithm has too many computations. So, we need a better processor or better computing unit. Yes, we need a better computing unit. The computing unit here is the NFU, right, that is actually performing the computation. But then if you see area wise, buffers are taking much more area than the computation, correct. So, in total all the buffers are taking like 30% of total 70% of the total area, which is huge, right. And then we may not be like speculating, or we may not be guessing that at the end of the day a good accelerator, or the area of a good accelerator, is mostly consumed by the storage, and that is why there is like bigger problem than computation. I mean memory is way bigger problem than computation when it comes to this DNN acceleration of the execution of DNN algorithms, right. So, not only area, if you talk about power, then also you can see that 22% is consumed by synapse buffer, then another 20% each is consumed by the NB in and NB out. So, like that is total like more than 60%, right. But at the same time NFU, the compute unit, is only taking 27% of the total power, correct. So, both area and power wise, computation might not be the bottleneck, memory can be the bottleneck. So, here the memory is nothing but this synapse buffer, input buffer, as well as the output buffer, right. Now, finally, whenever we talk about accelerator, we need to show that whether it really accelerates or not, right. Now, one goal of the accelerator is to reduce the execution time, another goal is to reduce the energy footprint, right. If we reduce the execution time, but then at the end of the day if we consume more energy, then probably there is no like we are not hitting the right trade off, correct. So, in this particular graph, they are showing the energy reduction over SIMD. Again, SIMD is nothing but single instruction multiple data, which is the typical operation principle of GPUs, right. So, they are showing the energy reduction of SIMD of course by DianNao for different types of layer like classification, different convolution, then different pooling. Again this I am assuming that these layers are coming from the ELINet network. So, as you can see that all the layers have very good amount of energy reduction with respect to SIMD processor or SIMD type processor, right. So, for an example, if you see this convolution 1, it has like 28 times improvement in terms of 28 times improvement in terms of energy. Now, why does it have that very high improvement? It has so many optimization, right. It is a very specific processor. DianNao is a very specific processor for the convolutional neural networks. So, it has like curated all these buffers, this neural functionality in such a way that the transaction or the data flow is so smooth, there will be the latency will be less and all those things, and then again the memory access is also reduced, correct. So, that is one of the biggest advantage of this DianNao architecture, that they have the split buffers, right. As I already told, if we have split buffers, then there is less contention, correct. If we have less contention, then there is less latency in terms of memory access and all those things. Okay. So, overall we have seen that we have seen this DianNao accelerator, which is very specific for this convolutional neural network. It has optimizations which is tailored for convolutional neural network to reduce the latency, to reduce area, etc., and at the end it is providing very high benefit with respect to SIMD processor. So, that is all about this particular lecture. In the next lecture, we will see more about DianNao or the advanced versions of the DianNao, and then we will see more accelerators like Iris. Thank you very much for your attention.